Welcome to this demonstration of the ARM microcontroller security research as part of the ECATS project in the SSITH program. Hi, my name is Hugo Vincent. I'm a researcher in the security group in ARM Research, based in the UK. As part of the SSITH program, my team has been working with researchers at SRI International, led by Dr. Peter Neumann, and the University of Cambridge, led by Dr. Robert Watson and Professor Simon Moore, on a project to enhance security in future silicon. As you may know, ARM is the world's leading supplier of semiconductor IP, designing and licensing CPU cores and other IP to hundreds of silicon vendors all around the world. ARM is perhaps best known for the Cortex-A series of high-performance CPUs widely used in mobile, but our focus in this program has been on the ubiquitous Cortex-M microcontroller cores used in chips for just about every product category, from industrial embedded systems to automotive, wearable medical devices, RFID tags, etc. This ubiquity and criticality makes them a high-profile target for malicious actors. ARM therefore places a high priority on incorporating the best possible security features to these processors. However, these applications demand state-of-the-art security without significant performance, power, and area overheads, and without rewriting the software stack. This calls for innovative solutions and ongoing research. We have created an experimental extension to this architecture, adopting the CHERI protection model. Capabilities are a new hardware data type for representing memory, replacing the long-held convention of using integers as addresses and pointers. Giving pointers a dedicated hardware type enables the hardware to distinguish them from other data, and to store additional metadata such as bounds and permissions along with them. As in other capability-based security architectures, capabilities are unforgeable tokens of authority. Holding a capability means you have the authority to access the memory it relates to. The compiler can automatically derive and use capabilities almost everywhere pointers are used, and in doing so, we can address a majority of memory safety related vulnerabilities that are known to be pervasive in almost all software. We focus on memory safety vulnerabilities since major software vendors report that a majority of vulnerabilities that they patch are due to memory safety problems, and therefore the capability extension in the hardware, along with the compiler, has the potential to make software much more secure automatically. Please note that this extension is the subject of active research within ARM. We hope future products will adopt this technology after the research matures, but ARM are not making any commitments regarding commercial availability. To demonstrate the utility of extending ARM microcontrollers with CHERI, we have built a demonstration application modeling a smart energy meter using ARM's reference software and firmware libraries, including the Cortex-M software interface standard and ARM Mbed OS, an open source real-time operating system. The smart meter device comprises a microcontroller along with a metrology front end, a real-time clock, an external flash memory chip containing a file system, and a modem for talking to a wide area monitoring network. Firstly, let's look at the system running normally. Here we're using an architectural instruction set simulator to run this scenario. The top pane here shows the diagnostic output from the simulated microcontroller, and the bottom pane shows the energy company's monitoring output. You can imagine this would be part of their central monitoring infrastructure, and it's showing live energy data as reported by the simulated device. The attacker wants to gain the ability to execute their own malicious code on the microcontroller, but basic security precautions have been taken. The microcontroller is running code from on-chip memory, and the debug interface, the JTAG port, has been disabled. So the attacker needs to find a vulnerability in the software and exploit it. The networking code would be the obvious way in, but this has been thoroughly tested and the attacker can't see an obvious way in there. So she needs to be more creative and turns her attention to the external memory chip. Because this device is outside the security perimeter of the microcontroller and has a standardized interface, it is easy for the attacker to intercept this connection with low-cost tools such as a bus pirate. The file system software is written in C, and like most such software dealing with binary data structures, it does a lot of pointer manipulation. Consequently, like most such software, it inevitably contains bugs, and these can be exploitable. By manipulating the data stored on the flash chip, the attacker can change the data structure into something unexpected by the software. The file system programmer has made a simple mistake in their error handling logic, and with well-formed file system data this is never reached. But with malformed file system data, the attacker is able to trigger a buffer overflow, and that's how our exploit is going to work. This was in fact a real vulnerability found in ARM's LittleFS embedded file system, and it has now been fixed upstream. We start by considering the existing Cortex-M architecture without the CHERI extension. The attacker constructs a malformed file system image and installs it to the simulated flash memory chip. This triggers the bug and causes a buffer overflow that the attacker can use to gain control of the device. And in fact, they have gained full control over the device, able to print messages to the diagnostic output and send false data to the monitoring infrastructure. Unfortunately, buffer overflows and stack smashing, as in this exploit, are all too common. The root cause is the confusion between pointers and data, allowing the attacker to inject data that is erroneously interpreted as a code pointer. CHERI fixes this root cause as well as many other so-called memory safety violations through the use of capabilities. We've now switched over to the same simulation, but with the CHERI extension enabled. Here we can see, instead of the device becoming compromised, it traps and recovers from the attempted exploit by rebooting into a recovery mode, allowing the operator to push a firmware update. This example shows a real exploit against code from a real IoT software library by ARM. It is just one example, but it is one that is representative of a ubiquitous problem caused by the lack of memory safety in the C and C++ software that runs so many of the world's embedded systems. We think CHERI addresses a majority of these vulnerabilities and does so with acceptable overheads. ARM research are excited about the possibility of incorporating this technology into future CPU products after the research, development, and evaluation in the SSITH program concludes, and we thank DARPA for making this research possible. Thank you for watching this demo, and please join us in the office hours for questions or more details.